Hi, good morning, everyone. Okay, so let's get started. So, so this is what we're gonna do today. So first of all, I'm going to talk about the garbage collection. So actually, I have been speaking about the Rust memory management, and I have not done with it yet. So there are some remaining slides which I couldn't talk about in the last few weeks. But I just recorded those things in video and uploaded it into YouTube. So if you are interested in the remaining part of the Rust memory management, please take a look at the video. So I do not want to spend too much time during the class on the same topic. So I'm going to move on to this next thing, garbage collection. And after spending an hour or so, I'll give you some time to work on the next assignment, whose topic is exactly the garbage collection. So please understand this part, and with that understanding in mind, please work on this assignment. So whose details are already out, so in a separate page. The format is actually quite similar to the previous assignment. Basically, so I ask you guys to get together with a group and discuss what you have discovered for your programming language. So the format is quite similar to the previous one, but so just briefly check the specification before you work on them. So the only thing I have just added, well, actually today, is this green part. So in case you have already looked at this page before, well, which was released in the last few days, so probably many of you have not looked at this, but so make sure that you read this part, which is somewhat specific to this assignment, the second assignment. But anyway, so otherwise the format is well quite similar to what we have been doing in so far. Okay, so let me get started with this garbage collection. Okay, so the next topic is another way of automatically managing memory. So I have been talking about Rust, but this time garbage collection used by many programming languages, including Go, Julia, and OCaml, and Python, and many other programming languages. So this is topics I'm gonna go through. So first of all, I'm going to talk about the criteria for evaluating garbage collection. So before we talk about various techniques to make garbage collection in some way better than more basic schemes, I need to address in which sense I'm saying this is better than the other. So let me first address what are the criteria with which we say this garbage collection is better than the other. And then I'm going to talk about two very popular traversing garbage collections, Mark and Sweep and copying. And I'm going to address the most important performance criteria of a garbage collection, which is memory allocation cost. And then I'm going to talk about two somewhat advanced garbage collection techniques. One is generational garbage collection, and the other is incremental garbage collection. I hope I can finish the first three sections before I give you a time to work on the exercise, because these three topics are very relevant to what you will be doing for the next assignment. Okay, so first of all, the criteria of evaluating garbage collection. So this is not, of course, the exhaustive list of criteria with which we evaluate garbage collection, but there are, broadly speaking, there are the following four criterions. So one is something called a preciseness. How precisely each memory management scheme is able to identify garbages. So memory. Second one is memory allocation cost, the work required to allocate a unit amount of memory. Well, obviously, this is in a way, the most basic and most important performance criteria. Yet another is something called the pause time. The time the mutator, the user program has to temporarily stop for the garbage collection to function correctly. So we usually talk about the worst case time. The user has to stop. So the basic thing is, so garbage collection will be working on the user allocated memory. So if the garbage collection concretely works with the mutator, something wrong is going to happen. You can easily imagine something wrong is going to happen if the mutator is a mutator under the user program and the garbage collector are working simultaneously on the same object graph. So the user, generally speaking, the user has to stop temporarily, at least temporarily, so that the garbage collection functions correctly. So the worst case time the user has to stop is called the pause time. And the last one is something called the mutator overhead. The overhead imposed on the user program for garbage collector to function properly. So I'm going to through the list again. The first one is what I call the preciseness. So when we compare well, generally speaking, I'm going to compare the reference counting and the traversing garbage collection. So when we compare reference counting and traversing garbage collector, generally speaking, reference counting is in a way worse. Traversing garbage collector is better in this respect. Primarily because reference counting cannot reclaim a cyclic garbage. So this is one thing I have already mentioned in earlier weeks. So take a look at this object graph. So in the case of traversing garbage collector, it identifies all the object that is reachable from this route. As a result, it is going to identify these orange objects as reachable from the route and identify other things as garbage and therefore collectible, reclaimable. But in the case of reference counting, which maintains the number of references each object is pointed to, these pink objects, these pink objects are not going to be collected, despite they are actually unreachable. They are not reachable from the route, because there's this cyclic references. So they point to each other so that no objects will have the reference counts of 0. So those green objects are going to be reclaimed. So let's say the reference count of this particular object drops to 0. Then this guy will be collected. And when this guy will be collected, after this guy is collected, reference counts of these two objects will also drop to 0. Then these two objects will be collected too. and this continues until this object. So after these green objects are collected, this pink cycle will remain. So any of these objects does not have a reference count of 0. So they are not going to be reclaimed by difference counting. So this is a crucial disadvantage of reference counting. So in terms of preciseness, the kind of garbages that can be collected, reference counting has a downside or drawback. So the second one, memory allocation cost, which I said will be the most basic and in some sense the most important performance criteria, memory allocation cost. It is actually difficult to say in a few words. Either one is better than the other. So more details will be ahead. But generally speaking, this is what I'm going to get into shortly. But in the case of traversing garbage collection, the cost will be determined by the ratio between the amount of reachable objects and the amount of unreachable objects. So I'm going to get into this later shortly. But if we accept this proposition for now, this cost will totally depend on the applications. The amount of reachable objects maintained by the applications and the amount of memory space this particular program is going to use. So those factors will determine this ratio. So it's difficult to say in a few words what is the cost of allocating memory with traversing garbage collection. And there's somewhat advanced technique to make this ratio smaller so as to make the garbage collection and the allocation cheaper or faster. This is something called the generational garbage collection, which I'm going to get into in the later part of this slide deck. And in the case of reference counting, basically, the cost of reclaiming an object once its reference count drops to 0 is small and constant. So it basically maintains the number of references to each object while the program is running. And once it identifies a certain object has now a reference count of 0, then it immediately reclaims it. And the cost is basically the constant. And the reclaimed memory can be used for further allocation, subsequent allocation. So generally speaking, the memory allocation cost is constant, no matter how much reachable object the particular application maintains or how much the total memory size that the program is using. So it is basically constant. And even if memory is scarce, it is generally good. So I'm going to get into this later. So the third criteria was pause time. And generally speaking, reference counting, the pause time is smaller than the pause time of traversing garbage collection. So in terms of which one it tends to be better, then reference counting tends to be better. So the reason behind this is traversing garbage collection. So this stems from the way traversing garbage collector generally works. So as I suggested several times already, without getting into details, it works by traversing all live objects. So all reachable objects from the root. And only after all reachable objects have been identified, can it reclaim a single byte of memory, right? So it basically works by identifying all reachable objects, after which it reclaims all memory blocks that have not been visited, right? So while the garbage collector, traversing garbage collector, is traversing the graph of the entire reachable objects, the application basically has to stop. So there are some ways to make it better. I'm going to get into this later, something called the incremental garbage collection. But generally speaking, you can easily imagine that you encounter trouble if while the garbage collector is traversing the graph, the mutator is changing the object graph, right? So you can easily imagine this is causing the trouble. So basically, the application has to wait and stop while the garbage collector is traversing the object graph. So in other words, it works by doing the whole bunch of work to get a whole bunch of free blocks. So it does not incrementally find the memory block that are not reachable. Yeah, like I said, so yeah, it was written in the slide. So you can easily imagine that you will encounter some troubles if the mutator runs to change the graph of object while the garbage collector is traversing the same graph, right? So a clever solution to this is, like I suggested already, something called the incremental garbage collection. And the generational garbage collectors are sort of mitigating this problem too, but for different purposes originally. But on the other hand, reference counting works by maintaining the reference counts of each object while the application is running. And while the application is running, when a certain object's reference count drops to 0, then reference counting memory manager can reclaim that particular object immediately, right? So it doesn't have to do the whole bunch of work to identify memory blocks that are not reachable from the root, because it always maintains the reference counts of each object. So basically, in other words, it can reclaim garbage as they arise. So this not a long period of time. The application has to stop for the memory manager to work. And finally, this is about the mutator overhead. Generally speaking, a traversing garbage collector has a lower mutator overhead compared to the reference counting. But this could be understood by understanding how the reference count actually works. So like I said repeatedly, reference counting works by maintaining reference counts of each object along the way. So while the mutator program, the user program is running. So for example, when you have an assignment like this, the reference count of the object pointed to by P will be decreased by 1 because the pointer to that object will be overwritten by this assignment, right? So you have to do something like this. And conversely, you have to increment the reference count of the object pointed to by Q, because now it is referenced by both variables, P and Q. And well, this doesn't sound too costly, but as a matter of fact, this is even more costly when the program is multi-threaded, because there may be other threads that are trying to do to the same on the same object, right? And you have to also care about the rare occasion in which this counter overflows. So if you deal with these things, this difference counting and the difference count management becomes even more costly. So there are techniques to mitigate this. I'm gonna get into this probably during the lecture. But generally speaking, maintaining difference counting is costly. So here's a small summary. So in terms of whether traversing or difference counting, generally speaking, better than the other. This is the summary. And there are some remarks. Well, so there's so many footnotes speaking about the cost of traversing garbage collection. So allocation cost, like I said, depends on the size of the reachable graph and the amount of memory you are using. And to reduce this allocation cost, something called generational garbage collector generally helps. And to reduce the pause time, something called incremental garbage collector generally helps. And for the muted overhead, difference counting generally is worse than traversing. But a caveat is that if you introduce a generational or incremental garbage collectors, they actually impose some muted overhead. So the picture is not as simple as this is better, always better than the other. So I'm gonna go to the next section, which is about two most popular traversing garbage collections. One is mark and sweep, and the other is called copying. Well, actually, they are in principle. So in principle, they are very similar. Well, both are actually finding all the nodes of the graph reachable from a particular node, which is root in the garbage collection terminology. So they are actually doing, so they are actually both doing graph traversal. So imagine you are asked to write a program that finds all nodes of the graph reachable from a particular starting node. So this is what traversing garbage collector is doing after all. So in that sense, mark and sweep and copying, yeah, in principle, almost identical, but they differ in what to do with reachable objects that they discovered. So in the case of mark and sweep garbage collector, it simply marks them as visited. On the other hand, in the case of a copying garbage collector, it copies them into a distinct contiguous region. So in a sense, mark and sweep garbage collector is more like just making the list of all reachable nodes. Whereas in the case of a copying garbage collector, it is making a copy of the graph, the part of the graph that turns out to be reachable from a particular node. But other than that, they are conceptually very similar. And all they are doing is, well, in a way, just a graph traversal. So this is how the mark and sweep garbage collector generally works. So they generally consist of two phases. People understand them as consisting of two phases. So one is called mark phase, and the other is called sweep phase. But actually, mark phase is doing the most essential job. So it basically traverses all objects from the root, and it marks object along the way. So it marks object as visited. whenever it encounters a new object. So this can be easily illustrated by a figure like this. So let's imagine this is the root, global variable or local variables of currently active functions. And these edges represent pointers. And imagine there are pointers between objects like this. So all you have to do is just to identify all objects reachable from the root by traversing one or more pointers. So in the beginning, it will discover that this object is reachable because there's a pointer directly from the root to that object. Similarly, it also discovers these two other objects are also reachable. So we are not done yet. We are not done yet because so you also have to discover object pointed to by this object because this one is also reachable from the root, right? By traversing pointers twice. So to that end, the mark phase continues by picking up any object that has been visited, that has been marked, and finding other object directly pointed to by this object you just picked up. So you simply continue doing this. So you do the similar thing on this object to find two more objects that are reachable. You keep doing it on the third object to find that this one is also reachable from this object. But you also discover that this object has already been marked. So you don't have to work on this object again. So for that purpose, you have to explicitly mark each object that you have visited, so that you do not duplicate the work again. But otherwise, this is as simple as you just keep doing it until you no longer discover new objects that are reachable. So I didn't explicitly mention the underlying data structure for that to happen correctly, but well, actually the important data structure is something called the mark stack. Not shown in this figure, but the mark stack basically maintains objects that have already been marked, but whose children may have not been marked. So during the marking phase, a mark stack is actually the set of light gray objects. So at this instant of mark phase, these two objects will be in the mark stack. These two objects are important because you have to work on these two objects. Oh, I'm sorry. This state is not. Okay. So sorry. So at this point, these three objects, so light gray objects, are in the mark stack. So those objects are objects that have already been marked, that have already been found to be reachable by the garbage collector. But inside each object has not been examined yet. So by examining pointers in these objects, you may discover further reachable objects. So one important distinction between this light gray and the dark gray is this dark gray has already been examined. So the pointer from this object has already been examined. So you have already discovered that this object is reachable too. But by examining these objects, you may find further objects that are reachable. So these objects have to be somehow maintained, which is done by MarkStack. But after you have done this traversing, the mark phase, you simply reclaim all memory blocks that have not been marked. So it simply reclaims all memory blocks that were not visited or that were not marked during the mark phase. So one thing that you have to note here is that in the case of mark and sweep garbage collector, free memory blocks are not necessarily contiguous in general. So here's some free memory blocks, and here's another free memory block. So they have to be managed by an appropriate data structure so that you are able to find a free block of an appropriate size. So when you are asked to allocate, for example, 128 bytes, you need to be able to find an appropriately sized free memory block. So they have to be somehow managed in an appropriate way. I'm not getting into the details of how this is done by. This is generally called a free list, the list of free memory blocks. So this is the other one, how a copying garbage collector generally works. So like I said, conceptually what it is doing is quite similar to what the mark and sweep garbage collector is doing. With the only difference being that copying garbage collector, as its name suggests, copies a graph of objects that turned out to be reachable from the root. So in that case, you simply imagine you are asked to write a program that copies a graph, maintaining the topology of the graph. So again, the only complication that arises that there may be multiple paths to the same object, right? So when you find a particular object to be reachable for the first time, you copy it. But next time, you may reach the same object from a different path. But in this time, you shouldn't copy the same object again, right? So you have to identify that you have already copied this object, and you also have to maintain that where this object has been copied, right? So that the same pointer in the original state must remain the same after you have copied the entire graph. So this is the only complication that arises. So this is most traditionally done by something called semi-space garbage collector. So copy all objects reachable from the root into another space that has, generally speaking, that has the same size of the original space. So this is where the objects have been allocated. And when this space becomes full, a garbage collection happens. And the purpose here is to copy the entire part of the graph that is reachable from this root to this two space. But other than that, what you are doing is essentially the same as mark and sweep case. So like before, we first identify that this object is reachable because it is directly pointed by the root. But this time you make a copy of this object. And two important things happen here. So one is obviously you have to redirect the original pointer, the pointer that used to be pointing this address to the new address to which this object has been copied. And the other thing is, this object may be visited again later, right? So when that happens, we have to know, we have to be able to know that this object has already been copied so that you do not copy it twice. And also you have to know where this object has been copied, right? So for that purpose, copying garbage collector installs a pointer to the new copy of the same object in the original object. So this is something called the forward pointer. So forward pointer tells you where this object has been copied earlier in the same garbage collection. So, but otherwise, it simply keeps doing the same thing. So we work on this object, copying it to here, and it further identifies this object to be reachable and copies it here. So until you are done. So after you have copied all objects that are directly pointed to by root, now you start working on these three objects. So again, this is somewhat similar to what I described as a mark stack in the Mark-III garbage collection. So these are basically objects that have already been identified as reachable from the root, but have not been examined by the garbage collection. So by examining pointers in these objects, you may find further reachable objects from them. So we need to keep working on this object. But naturally, we start with this first object. So you simply look at this object, which is the same thing as looking at this object. So by looking at this object, you are going to discover this object will be reachable too, right? So like before, we make a copy of this object, making a forward pointer to it. And also you redirect the pointer originally pointing this address to its new address. So you just keep doing it. So the next object you will be working on is naturally this guy. And you simply keep objects that are referenced by where this guy came from. So this guy came from here, right? So by looking at this object, you identify these two objects to be reachable. So therefore you copy these two objects, right? So you simply keep doing it until you have no more light gray objects to work on. So at this point, the copying phase finishes. And interestingly, what happens in the case of copying garbage collector is you have a contiguous free region. So you simply resume the application, and the application simply keeps allocating memory from this contiguous region. So unlike Mark and Sweep collector, you do not have to do anything complex to manage a free space. You simply allocate memory block from this contiguous region. And if memory allocation reaches this point, you simply flip the role of this to space and from space. So you simply triggers another copying garbage collection to copy all reachable objects from the root from this space to this space. So this is how copying garbage collector generally works. And yeah, maybe I don't have to get into details, but in terms of the code, this looks like this. So the entire copying garbage collector simple starts from doing something called the redirect pointers to the root object. This is doing exactly what I described in the beginning of this phase. But basically, you copy these three objects to this two space and redirect all these three pointers to the new space. So this is what happens in this redirect pointers root. And it continues working as long as these two pointers, so the two important pointers are something called scan and free. Scan basically points to the next object you have to work on in this two space. And free points to the address to which a newly discovered object should be copied into. So it keeps working until scan and free becomes the same. So if scan is smaller than free, it means that there is still at least one object you have to work on. So basically you pick the object pointed to by this scan pointer and apply the same redirect pointers procedure to this object. After you are done, a scan pointer will be advanced by the size of this object you have just worked on. So inside this redirect pointers, you are basically examining the contents of this object pointed to by this pointer. So basically, if you are given a scan pointer in this redirect pointers, then what you are doing is simply to scan each word of this object, see if it is a pointer, and check if the object pointed to by any pointer has already been copied or not. And if it has already been copied, you simply replace the pointer to its forward pointer. So where the object has already been copied. Otherwise, you copy the object as a newly discovered reachable object to this free address. So copy P to free. And install P's forward pointer to be the new address you have just copied the P into. And you increment the free pointer by the size of the object P pointed to. So, but this is actually exactly the same thing as copying a graph. So whether you are doing a garbage collection or you simply writing some application that is copying part of the graph for whatever purposes of the application, they are actually the same. So, here's some comparison between Merge-and-Sweep and copying garbage collection. So this is a pros of copying garbage collection. The disadvantage, advantages of copying garbage collection. So one remarkable advantage is that live objects occupy a contiguous region after a garbage collection. So after you are done with the garbage collection, these are live objects, right? So they become contiguous. So this is good for example, generally speaking, this is generally good for cache performance, for example. And the free region becomes contiguous too, right? So this is the live objects. This is the free region the application is going to use for subsequent allocations. Both are contiguous. So this is a very good point. So the reason why this is good, especially the reason why it is good for the free region to be contiguous is that the memory allocation is very cheap. The memory allocation becomes very cheap. So you don't have to do anything to search for a free region of a particular size. So when you are asked to allocate, let's say, 1,000 bytes, you don't have to search the free list to find a free block at least as large as 1,000 bytes. The allocation always happens from that contiguous region here. But there are some disadvantages. Well, so one is that copying operation is obviously expensive. So compare this to just marking an object as visited. So it is essentially setting a single bit somewhere in the memory. But copying garbage collection needs to copy the entire object, which is much more expensive than just marking the object as visited. And the free region must be reserved to accommodate an object copied. So this is actually resulting in low memory utilization. So obviously, if you can understand by looking at this figure, this is the entire memory region the application has to use. So effectively, the only half of the memory can be used for useful purposes, right? So the garbage collection needs to happen when half of the memory is full. So if you see this entire thing as the memory allocated to you, right? So at best, the memory utilization is 50% in this very basic scheme. So generally speaking, copying garbage collection simplifies things, but in terms of the cost, it is not necessarily good. But some argue that this small overhead for memory allocation is the very important thing for programming language implementation, especially for very memory allocation intensive programming language like functional programming languages. Another disadvantage of copying garbage collection is that pointers must be precisely distinguished from non-pointers. Well, in other words, ambiguous pointers are not allowed. So ambiguous pointers are something that we are not sure whether they are pointers or not. Well, generally speaking, when you are just given, for example, 64 bits of word, you do not know whether this is a pointer or not, right? So this is the way that the computer generally works, right? So 64 bits is just a 64 bits. It may be a pointer to, for example, memory block, or it may be just an integer. So generally speaking, you cannot distinguish from pointers to non-pointers. So there must be some tricks, some particular representations of data so that you can know whether this is a pointer or not. So this is commonly done in the context of high-level programming language. So the most common technique is just to have always the last bit set for non-pointer data. So by doing something like this, you have to be able to precisely tell whether a particular word is a pointer or not. Well, if I was not clear enough. So the reason why we have to be able to precisely distinguish pointers from non-pointers is that we change pointers, right? So we redirect pointers, right? So by making a copy of this object, after making a copy of this object, we change the pointer that used to be pointing to this address to a pointer that now points to this new address, right? So if we do this for integers, for example, it is a disaster, right? So you have to do this precisely for pointers and only for pointers. So this was not an issue for mark and sweep collectors. You can understand. So because it doesn't change the value of pointers in any ways. So this is the time I was supposed to finish. So actually, this is the main part, which talks about the memory allocation cost of traversing garbage collections. But so I leave this part for the next week. But in terms of the topic, this is somewhat related to the assignment you will be working on. But let's have enough time for your work. So let me stop at this point for this week, and so let's do the